All right, welcome back. It's good to see everyone this morning. One thought I had as we look at our schedule. Well, first off, is we're really in the home stretch here. It doesn't feel like it, but we are. It's going to be November by the end of this week, and we just really have these last 4 weeks together. These last kind of 12 Zoom meetings that we have remaining here. Not asking you to shed any tears today, but just in interest of looking at our schedule and what it's looking like here. It may be a good use of our time to spend some time debugging as a class our project Bs this week. So something I'll post a suggestion that if you're interested in doing so, we can hold a little debug party in class on Wednesday. So if you're in the middle of debugging project part B and you just can't get past a bug, that could be a good use for our time. That you share your code, I'll take a look at it before class. We'll try to walk through how I would go about debugging project part B bugs, and then from that example, hopefully you can then also on your own projects, if you didn't submit an example, can learn how to best debug those. That could be a good use of your time. It depends on where you are with regards to your project part Bs. There is that project part C that is coming. There isn't enough time in the rest of the semester for us to do that properly. So my plan is, and I have to discuss a little bit with the TAs. My plan is to scale that back. So there's an expectation of what is needed for a pipeline processor, but there just isn't enough time in the rest of the semester. So we'll scale back Project Part C so that it is something that can be accomplished in that 3 week period you basically have, with bonus extra points available for those who can do more or who are just really interested in doing more than what the required minimum would be for this semester. But other than that, we're almost done here. I mean that's a funny thing. So we're going to really cover our pipelining and control, and then we're going to make sure we do talk about cache memory. It's a little dry, it's a little basic, and that's okay. It's a necessary thing to know about to say that you've understood computer architecture, and it's probably of all the topics we're talking about, probably the most important from a software implications on performance perspective. So it will be important for us to cover it, and then the semester will be over, and you'll get your multi-month long break between semesters here. Um, but anyway, that's where we are right now. So we haven't really even started this topic yet on hazards and control. There's been some questions about it. People are getting close to that point, and maybe some of you have read ahead, which is great. But we haven't really talked about it at all. So let's cover it in some detail today, and depending on if we do some debugging on Wednesday, we'll then either finish it up on Wednesday or extend that into Friday. That's 4.7 to 4.8 of your textbook. Um, that note down there is actually wrong. Homework 9 is already out. You have 2 weeks to work on homework 9. Not because it's any longer than homework 8 was. Just we haven't gotten to any of these topics yet. So you can start homework 9. You can finish it if you'd like to, but you can also wait a week and you'll be fine with homework number 9. And those are very similar questions to homework 8. Tracing code on a pipeline, but it's more about now understanding the performance implications of doing that. Whereas homework 8 was just, do we understand how a pipeline works? Do we understand the data that's flowing through our pipeline for homework number 8? So again, we talk about hazards, and let's talk about what we mean by that. So the somewhat rhetorical question here is: we talked about even before our last exam here. Pipelining is a good thing, right? It gives us some of the best benefits of our multi-cycle processor, in which we've partitioned our critical path and have a faster clock frequency. With some of the benefits, at least in theory, of our single cycle processor, we can complete an instruction every single cycle. So we get both a good CPI as well as a good clock frequency. And so in theory, our performance should be faster than either our single cycle or our multi-cycle implementation. But we already started to see, or people were asking some questions about, well, what if I do this and do this? Won't this break the pipeline? And breaking the pipeline is what we're talking about when we refer to this term called pipeline hazards. Uh, whether that's a correct technical term or not, it's the textbook term being used to describe when something is not going to work properly, when our code will be wrong if we don't take extra care in how we execute it on the pipeline. The textbook talks about 3 major flavors of hazards. We'll very briefly talk about structural hazards. Possibly there is a way we could have covered this in a different order in which structural hazards would be more relevant for us. But in terms of our implementation, we'll see that we've already built it such that we don't have any structural hazards in our MIPS 5-stage pipeline. But the data hazards and the control hazards is what we'll spend our time talking about um, for the remainder of this topic here. Data hazards refer to when there's an attempt to use some data before it is actually ready, before it's actually a correct value that's been perhaps written back to memory or written back to the register file. We'll differentiate between what's referred to as data dependencies, which are the cause of data hazards, and the actual hazards, which refers to our pipeline execution, leading to incorrect results if we don't take special care and architect additional features. So that's that middle category, that data hazards. And the third one is control hazards, which can actually be thought of as a data hazard where the data that there is a dependency on is the program counter. But thought of it in a separate context, control hazards are attempting to determine what the next instruction should be and not having all the information we need to be able to make that decision. We can think of it just in terms of branch instructions, right? We have a branch instruction. It may take us a couple of cycles in our pipelined execution to know whether or not that branch should be taken or should not be taken. Well, what do we do in the meantime? Are we executing wrong instructions? And if we are executing wrong instructions, what do we do about that? And there's a whole lot of approaches taken to resolve control hazards as well as to take care of data hazards. One approach that always works, and what we will talk about this today, is to resolve our data hazard just by waiting. So detecting via some detection mechanism that there is a data or a control hazard, and we'll talk about the mechanisms we would instrument to be able to do that detection. We know it when we see it. Like when we're looking at a piece of code, we'll know that there's a problem, and then we just have to kind of translate that to architecture language for how we would build a unit to do that detection. But one approach would be just to wait. We know there's a data that's being written to, and we're going to have the wrong information if we execute this next instruction right away. So as a workaround, one such workaround is just to wait. Wait as many cycles, clock cycles as it needs for that previous instruction to get done or get sufficiently done so that our data is there when our next subsequent instruction needs it. That is one approach we can take. It's not a very satisfactory approach because if we have to wait and be waiting all the time and be so-called stalling our pipeline all the time, we're losing a big chunk of the benefit of having a pipeline processor in the first place, right? The idea is you have this full laundry pipeline, right? And you're constantly doing laundry or you're constantly executing your instructions. And if you have these waiting scenarios here, that does really very much defeat the purpose. So our goal is to be able to detect when there's these dependencies that could lead to the data and control hazards, and ideally is to build mechanisms that not only do that detection, help us resolve those hazards without having to just wait. Because that always will work as a solution. It's just not a very satisfactory solution from a performance perspective. Very briefly, when the book talks about structural hazards, and I'll bring this up here, it's referring to things such as if we only had one memory module. In the multi-cycle implementation, we only had the one memory module because we could multiplex it very easily. It could act as an instruction memory in cycle 1 and as a data memory in cycle 4. That's fine. Now in our pipeline implementation, we can't do that anymore. We've already made that decision, I think, when we were talking about pipeline layout a couple of weeks ago. But if we were to have just one memory module, we would see that the structural hazard would exist here because we'd be attempting to use it twice in a given cycle. And that's one of the concerns we have when we talk about structural hazards. We have these functional units in our pipeline, and we need to make sure they have really just one task in any given cycle. For everything else, it's okay. Everything else is kind of laid out so that we're doing one thing at any given time. But for memory, if this was the same physical port here as it is up here, that would in fact be a structural hazard. Our resolution is kind of a natural thing. We've already built it for our project part B um, single cycle processors. Just by having a separate data and instruction memory, we don't have those structural hazards there. Register file access is potentially also a structural hazard, just in terms of our shading of our pipeline diagram here as we're tracing through instructions here. It's been a few days. I should mention that this is going to be our way of very easily reasoning about what's happening in the pipeline, right? We show our time kind of progressing from left to right here, just cycle count by cycle count. That's these dashed lines referring to the different cycle counts. There was some definite ambiguity in that homework 8 question where it's asking about clock cycle 5. Is it asking about the beginning of clock cycle 5? Is it asking about the end of clock cycle 5? It doesn't really matter. Just say which one you chose and answer the question accordingly. And then on our so-called y-axis here, this is also time in a sense, but this is our instructions in our instruction memory layout as we're executing one instruction to the next. So this kind of graphical layout of the pipeline allows us to reason about what's happening in the pipeline from one instruction to the next without having to draw the entire thing. I mean, a lot of the detail is there. You can see like instruction memory leads to a fetched instruction that has some addresses for my register file to read from my address. It doesn't have all the details. We know we're missing the immediate input and all that, but it shows how those register inputs are going to the ALU, and potentially if it's a store word, that's also going to the memory port for the store word instruction. Otherwise, our address is going to the data memory. We potentially don't even use the data memory at all. And in fact, we want to write back to the register file. So it's a simplified sort of graphical representation of what's happening in our pipeline. And it does allow you to answer questions such as in clock cycle 5 for this block of code that isn't doing anything particularly interesting yet. What is happening in my register file in clock cycle 5? And we can see that in clock cycle 5, what is happening is that we're using the register file into instructions. That's potentially a hazard. But I think it's an okay hazard in the sense of the way we've already built our register file, in which for our implementation, we have a combinational read of the registers, and it's only our writing that is a synchronous operation. You can think of it as the write happening at some point during our clock cycle, and the read being this continuous operation. Technically, for that reason, we only have valid data in our register read operation in the second half of that cycle if we have this scenario in which those two instructions are both accessing those registers. But the way our clock synchronous design methodology has been working so far is we wait for everything to settle down anyway, right? We wait for everything to settle down anyway. The fact that it's half a cycle in which the data is valid versus the entirety of the cycle, we're not really modeling those delays in any case. So it doesn't really matter from our perspective of building a functionally correct pipeline processor. Has some implications on the clocking and critical path and all that. But in terms of a structural hazard, the way we've built our single cycle processor, as you now will be taking that and converting that to a pipeline processor, that issue with data memory as a structural hazard and with the register file as a structural hazard are kind of resolved for us. So that's all we need to know about structural hazards. Um, Other structural hazards could exist if we had wanted to use the main ALU for our PC plus 4 unit in the multi-cycle processor. We were able to do that, but now we can't anymore because that ALU is potentially being used by an instruction that's in the ALU phase. We can't both use it here as well as use it down here for PC plus 4. That's why, like in most likely your single cycle implementation, you're going to have a lot of these extra little one-off adders in there to deal with our next PC logic. We can no longer use the main ALU for that anymore because it has a dedicated purpose, and every clock cycle it's being used for that dedicated purpose. So it's the data hazards and the control hazards we care more about. Let's talk a little bit before we talk about solutions for data hazards. Let's talk about the nature of why they exist. What do I mean when I say when we have a data hazard? Um, if we don't do anything to architect to detect it and at least stall, if nothing else, we're gonna have a hazard. We're gonna have code that is incorrect on our pipeline processor. I know for some of you, you already were picking up on this a couple weeks ago, and maybe you've already caught it. But for the rest of us, let's take our time and walk through this example in some detail here. As we visualize our pipeline, where time is progressing from left to right here, that's our x-axis as we're showing clock cycle to clock cycle here. And our y-axis is our instructions as we're fetching and going through all the stages of execution. It will be a very common and a natural occurrence to have these dependencies between register values in our instructions. Dependencies meaning the value in a subsequent instruction depends on a value produced in a previous instruction. That's what I mean by dependency. They depend upon each other. Visualized here as these colored arrows going between one instruction and subsequent instructions here. Looking at just register 1 in this example, And I know the instructions don't have, at least this one doesn't have all the details because we don't need to know all the details for this one. We have an add instruction. And I know it's late in the semester and we still sometimes have to kind of look back and remember, well, which one's our destination? The first register is our destination here. So this instruction is writing to register one. That's what I want you to consider for this. Whereas because it's the second operand, and it could have been the third operand, because it's the second operand for the subsequent instruction, these are being read. These are the RS field for those subsequent instructions. That is, there's a couple ways we can label what's happening here. That is a data dependency. And I think it'll be worth our while to spend some time talking about the different flavors of data dependency. But that is, to start with, that is a data dependency. That is specifically referred to as a read after write data dependency. And I'll make sure I write this down so you're not just having to memorize what I'm saying here. A read after write data dependency, meaning there's a dependency of the data being used between any pair of instructions, and that's a specific order that is our dependency here. We are reading this value from register 1 after we've written our value from register 1. Okay? So it's both a dependency, and in our case, if we are not careful, it is also a hazard. The two terms are related, but they're not exactly the same, right? A data dependency is when we just have a relationship between instructions based on shared data. In this case, register values. A hazard, and it's a data hazard, is when our pipeline is broken because of a dependency. So we have this dependency in which we need to write to register 1, and for subsequent instruction and instructions here, we need to read to register 1. And as we just visually lay out our pipeline here and trace what is happening, those arrows that are moving so-called kind of backwards in time are what are our cause of our hazards here. And you don't necessarily have to overthink what's happening here. Our code's just wrong if we're not careful, right? You as a programmer wrote this pair of instructions. And you did so because you wanted to write a value to register 1, and you wanted that next instruction to use that value of register 1. That's a very natural thing we do when we're writing code, right? It's not a weird one-off extreme case that I'm positing here, right? So we want to write to register 1, and then we want to use that value to register 1. But in this instruction, because it's now in a pipeline processor, where our throughput is a lot better, but our individual latency of instructions is still roughly the same as what it was in our single cycle processor, it's not until the end of cycle 5 that we've actually, or at some point in cycle 5, that we've actually written to our register file, our write back stage of our execution. But for that next instruction, and for a couple of the later ones as well, it's not until this instruction's cycle 2, or cycle count number 3 overall, or it is at that point at cycle count 3 overall, that's our instruction read stage. Our register read stage, right? Where we've decoded the instruction, we know our RS and our RT fields and whatnot, and we actually connect those to our register file, like you already are for your single cycle processor, and you're reading those values from the register file. Those values that are in the register file corresponding to register 1, there's something there, but they're stale, they're old, right? They're from the programmer's intents perspective. You wrote this instruction followed by this instruction, and maybe I'm belaboring the point here, but you wrote this instruction followed by this instruction, presumably because you wanted this value to then be used in that next instruction. That's why you wrote the instructions in that order. If we don't take some special care here, you will have an instruction that in theory updates the value of 1, and it does so eventually, but when we get to that next instruction, and this is dependent on the depth of our pipeline and how many stages we split things into, and at what point in our pipeline we are actually reading from the register file, you'll have the stale values here. That's a hazard. Our code is wrong, right? You would have a result that you would expect as a programmer, and the actual runtime value of what gets written into register 4 here would ultimately be wrong if we're not careful. The same would be the case because the arrow is still kind of going backwards in time here for that AND instruction as well. You can kind of do a little bit of a hand-wavy argument and say, well, if we are actually updating our register file in the middle of that cycle, and we have until the end of this cycle, which is global clock cycle 5 here, to read from the register for that OR instruction, well, maybe that's okay. Maybe it just winds up working out just fine. And then I think clearly then it's the case that any instruction that happens after that point is going to be fine. Right? The value will be written here. That's at cycle 5. From clock cycle 6 until infinity, until we write to it again, we'll have the correct value there. We will have a data dependency still. This instruction and this instruction still have that type of data dependency, but we won't have that data hazard here. Um, let's walk through just some examples of what it means to kind of have those dependencies. Um, I think the point I want to make, and I mentioned it, but I want to make sure you see it here when we talk about our code here, is that data dependencies are just a very natural byproduct. It's not something that I'm setting up as an arbitrary example just to kind of trick you into worrying more deeply about your pipeline here, right? Here's a piece of, ugly C code here, right? Um, and this is just gonna be a very natural byproduct of writing code, right? We have variables, we create these variables, we write values to these variables in our C code because we want to use them, right? I mean, that's why you have a variable in the first place. So it's not a weird edge case that we're talking about here. It's um, going to be a very common thing that's happening in our code. And if we have our code laid out like this, we can kind of visualize that dependency is happening via that arrow that we have there, right? Um, and that's a very specific type of dependency that I've already mentioned, but we'll label it via its acronym as a raw dependency. And that's one of our 4 flavors of data dependencies. The raw dependency, that's a read after write. That is a programmer intended dependency that we expect when we write this code, that value of A on that second line that's circled there will be read after that same value of A was written to. That there's an implied ordering of our values that are happening here. I'll even add a little asterisk to this dependency because there's the 4 flavors of data dependencies. From our perspective, as we're worrying about pipelines and MIPS and all that stuff, um, that's the one that we care the most about. There are other dependencies that we would care about as we would explore more advanced pipelines, but you'll have a hard time seeing how that would be relevant as we look at our basic 5-stage pipeline here. In CPRE 581, depending on who's teaching it, a good chunk of the time in that course can be spent on advanced pipelining and how we resolve that. The textbook undergraduate pipeline we deal with is enough. There's enough complexity there. It gets a lot messier, in fact, as you have variable length instructions in terms of the number of cycles, as you have incredibly deep pipelines, as you have multiple instructions being issued in a given clock cycle. These other dependencies also become pretty relevant. So this is a dependency. We expect that value to be read after it was written. Well, let's make another code example and see if we can come up with some other dependencies that happen here. Yes, this is the font you should all use for all of your programming. If we just have like a for loop instead. What kind of dependencies do we see there? Make it a little larger and sideways. What other dependencies do we see in this example? Again, this is C code, so we're not talking about registers in which it's very obvious when we're looking at assembly code. We'll do the assembly code example as well. Any dependencies that we see here? So for control, there's okay. What kind of data dependencies we see there? So we will definitely have. So I would be a good example. Another way to think about what we're possibly seeing here is anytime a variable, or as we look at registers, anytime a register is used more than once in a block of code, which again will happen all the time, really, um, there is a data dependency there. It's a separate question of what type of data dependency is it. So we can identify those, and let's do that here now. And then it's kind of a third and equally important question to us. Okay, here's a dependency. Anytime the variable I shows up here in this code, it's a dependency. What kind of data dependency is it? And then is it of that asterisk class of dependencies up there that is going to cause us a problem in our pipeline. So those are all part of the same question, and it's probably easier when looking at MIPS than at C code for this, because the variable usage or the register usage is so explicit. But we can definitely do it with um, our register values here, right? We have just all sorts of dependencies here, right? We have value I. See if this works. Our variable I being dependent on variable I here, right? We would read I to calculate B of I, followed by reading I again, potentially to calculate A of I. That is not a read after write dependency because in both cases we're reading them, but maybe we can determine what kind of dependency that is, right? We're reading it, and then afterwards we're reading it again. That's a read after read dependency. There's going to be a lot of read after read dependencies here because this is a loop, right? And so because it's a loop, this is going to get ugly pretty quickly here. We could label that as a read after read dependency. Every time we use I, there's a dependency there. So we can start with just kind of circling all the I's here to begin with. You could argue A and B as pointers would also have, whatever the base address there is kind of a read after read dependency, or in the case of I, would also be a write after write dependency. But just looking at I to begin with here, we have a lot of potential dependencies here, right? We have I equals 0 next to, followed by, we do a calculation of I less than n. What kind of dependency is that? So our loop gets executed. We have to initialize I equals 0. We have to check if I is less than n. Yep, absolutely. We read it. We write it. After which we read it. We want to make sure we have to be concerned that the order is actually going to be correct here. There are a lot of read after write dependencies just based on that I equals 0 write of I, right? Because every time we want to actually use I in our code, we're reading it. Those are also read after write dependencies. Any other dependencies we see here? Yeah, I plus plus is kind of ugly, right? Because I think if we think of what's happening with I plus plus, it's really I equals I plus one, and maybe it's more clear to see if we were to write it as I equals I plus one here, right? Well, I actually shows up twice. There's a lot of dependencies there. Specifically, we do see that we have a read after write dependency with I plus plus. To be able to properly calculate I plus plus, we have to first read I, we have to increment I, and we have to update I. That's a read um, after write dependency. We have to we have to read I. We have to then update I. That is a write after read dependency. There, right? That's the order in which those operations are supposed to happen. We read from I first, then we update I. One could argue um, the MIPS pipeline was in part devised to avoid write after read dependencies as a design consideration. Our writes, I have trouble pronouncing this correctly. When we write data to our pipeline, our write operations in our pipeline always happen at the end of the instruction, right? There's a write back phase or there's a memory write phase, and that's the very last thing that our instructions are always doing in MIPS. And so, in theory, though, for a pipeline, that would be a dependency that's important to us. In practice, our writes always happen after our reads in MIPS anyway. So that issue of going backwards in time and having the wrong value, the ordering is already kind of required in our MIPS ISA. We don't have that issue with our implementation. Certainly, though, as we go from one iteration of a loop to the next iteration of a loop, any pair of these from one iteration to the next is a dependency. So we write to I and we write to I again in the next loop. That would be a write after write. Any combination of reading and writing to a variable is going to be a dependency there. Yeah, that new I is gonna have yeah, it's gonna be completely impossible to draw here, to be honest, right? Yes, absolutely. These are important ones, right? These are also going to be read after write dependencies here because we've written to I don't know, something like that. We've written to I, and we have all these reads that are happening after we've written to I. We absolutely have all those raw dependencies in that example here. It got ugly pretty quickly because it's a loop, and so we have to cross boundaries of the loop to see all the potential dependencies because the dependencies are in time. They're not just dependencies in terms of one line of code to the next line of code. It's from instruction to instruction or operation to operation in time that we have our dependencies. All your code, and maybe one of the takeaways from this would be all of your code is going to be absolutely littered with these kind of dependencies. That is just a natural byproduct of how we write code. It'd be very hard to write code that doesn't have dependencies, right? As soon as you have a variable, you've created it for a reason, and you've created it because you'd like to use it again. So because of that, you will have these dependencies, and it's good to be able to identify them. There's the four categories here for our pipeline implementation in this class. The only dependency, because of when our writes are happening in our data path, the only dependencies that potentially are going to lead to hazards are going to be these read after write dependencies. We can walk through the other examples. A read after read dependency, well, it doesn't seem like a big deal. Okay, I'm supposed to read the variable twice. If I swap the order in which I read that variable twice, should be okay, right? I read it once and I've read it twice, and I swapped the order and I've read it twice, and it's fine. It's the same value. It hasn't changed. Read after reads are only relevant in the sense that they are also part of these write related dependencies. Write after read is an important dependency, as is potentially write after write. If we do our writes in the wrong order, we would wind up with the wrong value at the very end. It just so happens in our MIPS ISA, where all of our write operations are happening at the very end of our execution of an instruction, that we never wind up having them in the wrong order as we do our basic pipelining here. But because we do our reads early in the instruction and our writes later in the instruction, we do have issues with our instruction execution of those potential read after write dependencies there. Um, it is, I think, arguably easier to detect these dependencies when we are looking at assembly code. And for the same reason, all we really have to do is to look at um, every time a register value shows up twice in an instruction, that's potentially a dependency here. So I just have a quick example here that I didn't have time to put on the slide. So we have an instruction that's writing to register. This is not a fixed width font, which is going to annoy me here. Okay, we have an instruction that's writing to register 3. And then we have, let's say, a load instruction, followed by another add immediate instruction. Followed by, let's just do one more instruction here. And I'd like your help. Help me identify some of the dependencies in this example. Let's make it a little bit larger and sideways. Okay. I, you know, the font is what it is. What are some of the dependencies that we have here? You can type in the chat. I could do breakout rooms, and then you have to write all this down in the first place. So let's just start with, just based on your input in the chat here, what kind of dependencies do we see? War for two. So I guess you're almost certainly right. But to describe the dependency, it's probably most helpful to say something like there's a dependency between instruction 1 and instruction 2 on register 2. Just to go with the first example you had here, which is correct. There's a dependency between this and this in this instruction, and it's a write after read dependency because we read the register for this, And you do have to remember your loads and your stores, right? Again, you have to remember which one's which and which direction the data is flowing in terms of register reads and register writes. That is important. That is why this is a write after read dependency, because we read it in instruction one and then we write it in instruction two. And I did tell you, and if I ask you to find the dependencies, that is a 100% correct answer. If I then am going to ask you, find the dependencies that are potential hazards, then we have to be a bit more specific. Seeing some good examples here. Um, line one and line two for two rar, correct. Line one and line three for register one as well, there's a lot going on here, right? Um, keep typing examples. So I like it. So line one we read to, and then on line two we write to. Yes, that's our write after read dependency. We got that one. Um, basically, and there's going to be a lot here. Anytime you seem to see the same register twice, any pair is a dependency. Any pair at all. There's an argument to be made for, well, this instruction is 10,000 instructions later on. Do we really care about the dependency? That's a different issue. But if I gave you 6 lines of code and said, identify the dependencies, that's absolutely right. Anytime the register 1 shows up, any pair is a dependency. Then your only challenge is, well, what is the actual nature of the dependency? First off. Second, again, is it a dependency that we care about from a pipeline hazard perspective? And then as we talk about it, more this week, what do we have to do to resolve that dependency, or do we have to stall? That's the thought process. But we started with just identifying every time the register 1 shows up, that is a dependency. Because register 1 shows up way too many times as an example, let's look at some of the other registers first, right? So register 2 shows up, I can't read my own writing here. Register 2 just shows up those 2 times, so we're done with register 2. Register 3 shows up a few times. We can identify those. So good messages in the chat. We're going to do a poll here. So I'm circling 3, and I'm circling 3, and you can kind of see the arrow I've drawn between 3 here. I would like you to click in your participant window there where you have those responses. Click thumbs up if that is a write after read dependency, and thumbs down if that is a read after write dependency, or click something else if it's something else. So thumbs up for read after write. Seeing a lot of people who are giving me a thumbs down. I mean, we have some. Let's give it a minute here. We have some split decisions here, and I didn't make it all that clear. So you may have the right answer and just click the wrong icon. Okay, it's I don't know if you can see it. It's a close neck and neck tie here. So for register 3 to register 3 happening here, this is our write operation. Right? We are writing to register 3 in that add instruction. Here in a load word, yeah, it looks funny because it's in the parentheses and all that, but we are definitely reading from that register for that load word operation. Right? That's our address. So no matter what's happening in the instruction, that's a read operation happening there. So that one is a read after write. And I don't remember if that was thumbs up or thumbs down. So you all get full credit. Nah, it doesn't matter. Okay, good work. So that's one dependency between 3 here. But anywhere else we have a 3 is also a dependency. This one, which is register 3, and this one here, is also going to be a read after write dependency for roughly the same reason. It's a further apart read after write dependency. I did say it both ways. It is a further apart read after write dependency. So maybe it's going to be less of an issue. That's the secondary question. The first primary question here is, what are the dependencies? What type are they? Finally, we have our, well, no, not finally here. We have our dependency between that 3 and that 3. That is very much a read after read dependency. Both instructions are reading it. Shouldn't be an issue for us, but it's there. It's a dependency that exists in our code. This has implication for the compiler as well. Compilers tend to refer to as define use chains of variables and registers, but these dependencies also limit to what extent the compiler can reorder instructions, which is a very powerful thing that compilers need to be able to do. It has to be able to analyze those dependencies for the same reason. If I were to reorder instruction 1 and instruction 2 in the compiler, the code would be quite different and presumably wrong as well, right? So that analysis is still happening here, but in this case, we're looking at it from a pipelining perspective. So we have those connections there. We also have this register 3 being written to here. What kind of dependency is that with that arrow just drawn between line 5 and line 6? Type that one in the chat. I don't trust us to do the responses correctly. Yeah, that one's a war one as well. Don't overthink it. We are writing to this after we've previously read from it. Doesn't affect our pipeline because it shouldn't cause us an issue, and you can trace through it yourself in the pipeline if you need to convince yourself of that fact. The writes are happening so late in instruction 6 that there should never be any issue in which it happens before instruction 5 does its read operation. That's why it's not an issue. And same with the write after write dependencies that we have here. But there's more, right? Just looking at 3, any pair of 3 is a dependency. That's also a write after read. And finally, for register 3, what is that dependency between line 1 and line 6? Yep, and that's a write after write dependency for that one. Sometimes they can be a little more subtle to identify. With Again, with load word, you do have to remember, and with store word, you do have to remember what is the instruction doing. So we're definitely at the point in the semester where I do expect you to know that. Have a little like sticky note on your monitor or something reminding you of that case as you're designing your processor and answering homework questions. There's too many dependencies in register 1 here to label them all out. But this would be an important one here. Between line 3 and line 4, what type of dependency is that between the two I circled? I know there's another register 1. Hmm. Well, we know it starts with the word write. Okay, so register 3, instruction 3 is writing to register 1 here. It's also reading, but ignore that for now. This example's got too much stuff going on. It's writing to register 3, certainly. Store word in this case, it kind of looks like it's writing to register 1, right? Because that's just what the instruction looks like, but it's not. It's reading from instruction 1 because it's a store word. It's writing it to memory, but in terms of its interface with the data dependency here, the dependency is on register 1. So that is very much a, as someone put, that is very much a read after write dependency. It looks like it's a write after write, but it's not because we're not writing to register 1 at the output. Register 1 does not change at the output of this instruction for that store word instruction. Some location in memory changes, which is relevant to us, but it's not the type of dependency that we're analyzing in our pipeline here. Um, there's very much similar dependencies for memory. They're not the kind of thing we can easily trace by looking at static assembly code here, but there's similar analysis that can be performed. It has implication for our cache design coming up, but it's a more solvable problem, I would say, than more complex pipeline dependencies here. There are many more dependencies here, but let's remember the 3 stages. So not the stages of grief, stages of data hazard detection here. Stage 1, if it's MIPS code, um, there's probably going to be the example I provided. You probably have too many to even pick out. But anytime the same register is being used in any pair of usages, that's a dependency. And so we could actually add up all the register 1 dependencies because there's 1, 2, 3, 4, 5 uses here. I think there's 5 choose to dependencies in this example, right? Because any pair is a dependency. Um, so that's step 1. Determine all the dependencies. Circle them all, I guess. Step 2 is then to label them, which is really just a walking through of as time progresses. If it's a loop, of course, it gets very messy, as our example did show. But as time progresses, at least in our kind of non-looping code here, what is the intended order of operations? That's what we're labeling our dependencies as. That's why it's a read after write between line 3 and line 4 here. We are writing to register 1, and we're wanting to read afterward. Read after write dependency. So that's our step 2. And specifically, again, given the four types of our dependencies here, they're all important to be able to identify and recognize. But from a CPRA 381 perspective, um, it's the read after write dependencies that we care about. And then finally, that third step is as we identify those, and we haven't really gotten through this part yet. Um, what do we do about it? Is what are the ones that we actually are concerned about? Um, when I say concerned, I mean what dependencies do we have to add more logic to our pipeline to detect and to hopefully resolve without having to stall, without having to slow down our pipeline. Question is asked, how far away can we have dependencies? Well, it depends on who's doing the analysis, right? The compiler tends to look at things at either the function boundary or the basic block boundary. So an entire for loop or an entire function call, and all the register analysis is fair game within those contexts. For our pipeline, it really is very pipeline dependent. For our MIPS pipeline, 5 should be sufficient, right? We don't care what's happening 6 cycles from now. It's our instruction will be completely done by the time something 6 cycles or 6 instructions from now is starting. So 5 or 6 is the limit of what we would ever care about for our MIPS pipeline. But if our pipeline was of a variable depth and that depth could grow to 47 stages, as is very often the case, well, then we really do need to have a pretty far horizon in terms of that dependencies that we're analyzing. Um, if it's a homework assignment, I will say, just identify the dependencies. And yes, technically, anything happening between instruction 1 and instruction 6 will never impact our MIPS pipeline because we're only going to have those 5 instructions in our 5-stage pipeline at any given time. But okay, step 1 is identifying the dependencies. Identify all of them, or I'll give you, identify 7 dependencies here. Step 2 is determining which ones are of which type, and then step 3 is which ones do we care about from an architecture perspective. And I think it would be fair to say the ones we care about are the read after write dependent data dependencies of some reasonable closeness to each other. Within those 5 instruction range are the ones that we care about. Um, I think that's actually probably a pretty good stopping point for today, right? So we went through an exercise of identifying those dependencies. We definitely need to talk about what we do in the case of those. Um, in this case, with this hazard here, these are all read after write dependencies that are being identified here. There's a lot of read after read ones that aren't relevant for our pipelines perspective, but this is our write operation. There's one, two, three, 4 read after write dependencies here. It turns out that some of them are going to be fine, right? Because they're sufficiently far from each other, the pipeline's caught up by that point, and so the dependency isn't going to get broken with our basic 5-stage pipeline. But for these two cases here, that's what we can look at either on Wednesday or Friday, depending on if we debug some Project Part B processors on Friday. We have to take some special care to make sure that this instruction and this instruction isn't operating with wrong data. And then finally, we will talk about this again. We'll start here again. When we have load instructions that are doing the write operation, followed by those read after write type of dependencies, that is a very special case of read after write dependency for the MIPS pipeline. Those are referred to as load use data hazards. And we'll talk about why that's the case, why this case, where it's a load instruction, is any different than the previous case where it's an add instruction. That's the only difference between these two examples here. It is a different case. It is just a different usage of our um, register write back. But because of where it's happening in our pipeline, where the value is in our instruction, we are actually going to treat those load use cases significantly differently than our add instruction, our R type data dependencies that we have here. This is probably a pretty good stopping point for us. So, you have a homework that starts to talk about these things. You don't really have to look into it yet. Definitely, this is a good week then because of the homework not being due at all to really, really dive into Project Part B between today and Wednesday. That would be great. If everyone hits a tough bug and needs my help, we should be able to make a lot of progress, between now and Wednesday, and then we can use our class time on Wednesday if you're interested in doing that. Otherwise, good luck on the project, good luck on all your work, and I will see everyone on Wednesday.